When a transformer's primary fuses blow upon power up, several factors could be at play. Two new installations experiencing the same issue suggests a common cause related to the transformer itself or the power supply characteristics. One primary suspect is inrush current. Transformers, when initially energized, draw a significantly high surge of current. This inrush current is needed to establish the magnetic field in the core and can be 10 to 20 times the transformer's rated current. Standard time delay fuses are designed to handle short duration overcurrents, but the magnitude and duration of the inrush current can overwhelm them, causing them to blow. Another contributing factor is the magnetizing current. This is the current that flows through the primary windings to create the magnetic field within the transformer's core. While essential for operation, the magnetizing current is reactive in nature. This can lead to voltage distortion, adding stress to the fuses and potentially causing them to fail over time. Insulation breakdown within the transformer can also be a culprit. If the insulation of the windings is compromised due to factors like moisture, overvoltage events, or mechanical stress, it can lead to partial discharge or arcing. This arcing generates excessive current that can blow the fuses. Finally, shorted windings, either between the primary and secondary windings or within the primary windings themselves, can cause a massive current surge. This could stem from a manufacturing defect or physical damage to the transformer during handling or installation. Addressing the issue involves several potential solutions. Firstly, consider using slow-blow fuses. Slow-blow fuses have a longer time delay compared to standard time delay fuses. This extended delay allows them to better withstand the inrush current without tripping unnecessarily. Secondly, installing a surge suppressor on the primary side of the transformer can help limit the inrush current and protect the fuses. The surge suppressor absorbs a portion of the initial surge, preventing it from reaching the fuses. Thirdly, reducing the load connected to the secondary side of the transformer can decrease the inrush current during startup. While not always practical, minimizing the load during initial energization can lessen the stress on the fuses. Fourthly, it is important to check the transformer's insulation resistance using a megometer. This test will reveal any degradation of the insulation, indicating a potential breakdown. If the insulation resistance is below acceptable limits, it suggests a need to replace the transformer. Fifthly, inspect the transformer for shorted windings. This often requires a qualified electrician to perform a more thorough inspection and testing of the windings. Shorted windings are a serious issue that necessitate transformer replacement. In your case, since the issue is occurring on two new installations and you've already ruled out the wiring, the transformer itself is the most likely source of the problem. Increasing the fuse size, as you've done, might mask the problem temporarily, but it does not address the underlying cause and could potentially lead to more serious issues if a fault condition occurs. It is essential to determine the root cause to ensure the long-term reliability and safety of the installation. Here's a more detailed breakdown of each potential cause and solution. Regarding inrush current, the magnitude and duration depend on several factors including the transformer size, core material, and the point in the voltage waveform at which the transformer is energized. Energizing the transformer at the voltage peak results in minimal inrush current, while energizing it at the voltage zero crossing results in the highest inrush current. Because this is random, the transformer can draw large inrush currents for a few cycles. Time delay fuses, sometimes called dual-element fuses, are designed to withstand short overloads such as motor starting currents, but inrush current can still exceed their interrupting capacity. Slow-blow fuses, also known as time delay fuses with an even longer delay, are specifically designed to handle high inrush currents. They typically have a higher I²T rating, which represents the amount of energy the fuse can absorb before opening. A correct slow-blow fuse should be selected based on the transformer specifications and the expected inrush current. A surge suppressor, also called a transient voltage surge suppressor, or TVSS, protects electrical equipment from voltage spikes and surges. They work by diverting excess voltage to ground, preventing it from reaching the protected equipment. For transformers, a surge suppressor installed on the primary side can limit the magnitude of the inrush current, protecting the fuses. It is important to choose a surge suppressor with an appropriate voltage rating and surge current capacity for the transformer's application. Reducing the load on the transformer during startup is a practical solution, particularly if the load consists of multiple devices that can be energized sequentially. By staggering the startup of these devices, the inrush current demand on the transformer is reduced. Insulation resistance testing is a critical maintenance procedure for transformers. A megometer, also called a megger, applies a high-voltage direct current signal to the transformer's windings and measures the resistance between the windings and ground, and between the windings themselves. A high insulation resistance indicates that the insulation is in good condition, while a lower resistance indicates insulation degradation. Insulation resistance values should be compared to manufacturer's specifications or industry standards, such as those published by the Institute of Electrical and Electronics Engineers, or IE. Inspecting for shorted windings requires specialized equipment and expertise. A qualified electrician can perform a winding resistance test to measure the resistance of each winding. Significant variations in winding resistance can indicate shorted turns within the winding. They can also perform an impedance test to measure the impedance of the transformer. Shorted windings will typically result in a lower impedance than normal. If shorted windings are suspected, the transformer should be removed from service and either repaired by a qualified repair shop or replaced. It is important to note that repeatedly replacing blown fuses with larger fuses can be dangerous. While it may temporarily solve the nuisance tripping problem, it also reduces the level of protection provided to the transformer and the connected equipment. If a fault condition occurs, the larger fuses may not trip quickly enough, potentially leading to overheating, insulation damage, or even a fire. The National Electrical Code, or NEC, provides guidance on the appropriate fuse sizing for transformers. NEC Article 450.3 covers the overcurrent protection of transformers, and it specifies the maximum allowable fuse or circuit breaker size based on the transformer's rated primary current. In general, the primary overcurrent protection should not exceed 125% of the transformer's rated primary current. For example, a 5 kV transformer with a 480 volt primary has a rated primary current of approximately 10.4 amps. Therefore, the primary overcurrent protection should not exceed 13 amps. The NEC also allows for the use of the next highest standard fuse size if the calculated value does not correspond to a standard fuse size. It is important to consult the NEC and local electrical codes to ensure compliance with all applicable requirements. In your situation, since the 10 amps fuses are blowing instantly, even with no load connected to the secondary, it is likely that the inrush current is significantly higher than the fuse's interrupting capacity. Using 15 amps and then 20 amps fuses might seem to resolve the issue, but it is not a recommended solution. It is important to investigate the underlying cause of the excessive inrush current. One possibility is that the transformer is slightly oversized for the application. An oversized transformer will have a lower impedance, which can result in a higher inrush current. If this is the case, consider using a smaller transformer that is more closely matched to the load requirements. Another possibility is that the supply voltage is unstable or contains excessive harmonics. Voltage fluctuations and harmonics can increase the inrush current and stress the fuses. In this case, you may need to install a voltage regulator or harmonic filter to improve the quality of the power supply. It is also important to verify that the transformer is properly grounded. A poor ground connection can cause voltage fluctuations and increase the risk of insulation breakdown. The grounding system should comply with the requirements of the NEC and local electrical codes. In summary, when transformer primary fuses blow a power up, it is typically due to inrush current, magnetizing current, insulation breakdown, or shorted windings. The most effective solutions are to use slow-blow fuses, install a surge suppressor, reduce the load during startup, check the transformer's insulation resistance, and inspect for shorted windings. It is important to avoid simply increasing the fuse size, as this can compromise the safety and reliability of the installation. Consult with a qualified electrician to properly diagnose the problem and implement the appropriate solution. Considering that you have two new installations exhibiting the same problem, there is a higher probability of a manufacturing defect with the transformers. Contact the manufacturer to see if there has been a batch issue or any known problems with the model you have purchased. If there is a known issue, you will want to replace the defective transformers immediately. Finally, remember safety first. When working with electrical equipment, always de-energize the circuit before performing any inspection or maintenance. Wear appropriate personal protective equipment, such as safety glasses and insulated gloves. If you are not comfortable working with electrical equipment, consult with a qualified electrician. Here are some additional points to consider. Firstly, ambient temperature can affect the performance of fuses. Fuses are designed to operate within a specific temperature range, and extreme temperatures can cause them to trip prematurely or fail to trip when they should. If the transformer is located in a hot environment, it may be necessary to use fuses with a high temperature rating. Secondly, altitude can also affect the performance of fuses. At higher altitudes, the air is less dense, which can reduce the fuse's ability to dissipate heat. If the transformer is located at a high altitude, it may be necessary to use fuses with a low current rating. Thirdly, the type of load connected to the transformer can also affect the inrush current. Certain types of loads, such as motors and capacitor banks, can generate high inrush currents. If the transformer is connected to a load that generates high inrush currents, it may be necessary to use slow blow fuses or a surge suppressor. Fourthly, impedance of the power source can also affect the inrush current. A low impedance power source will allow a higher inrush current to flow, while a high impedance power source will limit the inrush current. If the power source has a low impedance, it may be necessary to use a surge suppressor or a current limiting reactor. Fifthly, the transformer's nameplate data provides important information about its operating characteristics. The nameplate data includes the transformer's kilovolt-amps rating, primary and secondary voltages, impedance, and temperature rise. This information can be used to select the appropriate fuses and other protective devices. Sixthly, regularly inspect the transformer and its associated equipment for signs of damage or wear. Look for cracked or damaged insulation, loose connections, and corroded components. If any problems are found, they should be repaired promptly to prevent further damage or failure. Seventhly, keep the transformer clean and free of dust and debris. Dust and debris can accumulate on the transformer surface and reduce its ability to dissipate heat. Use a vacuum cleaner or compressed air to clean the transformer regularly. Eighthly, maintain a record of all inspections, tests, and maintenance performed on the transformer. This record can be used to track the transformer's performance over time and identify any potential problems. Ninthly, provide adequate ventilation for the transformer. Transformers generate heat during operation, and adequate ventilation is necessary to prevent overheating. Ensure that the transformer is located in a well-ventilated area and that there are no obstructions blocking the airflow. Tenthly, consider using a transformer monitoring system. These systems can continuously monitor the transformer's operating parameters such as voltage, current, temperature, and oil level, and provide alerts if any problems are detected. Finally, remember that transformer failures can be costly and disruptive. By following these recommendations, you can help to ensure the reliable and safe operation of your transformers.